Welcome to This Explainer. Today, we're diving straight into the ultimate cosmic detective story, the hunt for an invisible substance that quite literally holds our entire universe together. We're going to unravel a century-old cold case that's completely filled with missing evidence. We're talking about entire galaxies behaving in ways that completely defy classical physics. We'll be tracking invisible footprints across the cosmos and even venturing deep underground to massive particle detectors built to capture an absolute phantom. So get ready because we are launching straight into the search for dark matter. So I want you to imagine looking out into the vastness of space on a super clear night. The billions of twinkling stars, glowing nebula, those swirling galaxies, it all feels infinite, right? But what if I told you that every planet, every star, and literally every black hole combined is just a tiny, tiny fraction of the cosmos? The vast majority of our universe is actually missing. It's just hiding in plain sight. It's this incredibly unsettling realization that everything we can see, touch, and measure with our traditional instruments is really just the foam on top of a very deep, very dark ocean. And the scale of this mystery is genuinely staggering. If you look at the standard model of cosmology, ordinary matter, the stuff making up you, me, the Earth, all those radiant stars, it accounts for a mere 5% of the mass energy content of the universe. Just 5%. Now, dark energy, which is that mysterious force driving the accelerated expansion of the cosmos, that makes up roughly 68%. But right there in the middle sits our primary suspect, dark matter, coming in at almost 27%. It outnumbers everything we know and understand by over 5 to 1. It's the dominant form of matter in our reality, yet it entirely evades our senses. Section 1. The missing universe. Okay, so if we strip away dark energy for a second and just strictly look at the matter in the universe, the numbers become even more mind-blowing. A whopping 85% of the total mass out there is completely unknown to us. It doesn't emit light, it doesn't absorb it, it doesn't even reflect it. It completely ignores electromagnetic radiation. Its only known interaction is through gravity. But here's the thing, this isn't just some random piece of trivia. It's literally the very reason we exist. Back in the chaotic aftermath of the Big Bang, this invisible dark matter acted as our crucial gravitational scaffolding. It clumped together into these massive cosmic webs, creating immense gravitational wells. These unseen valleys of gravity then pulled all the ordinary hydrogen and helium together, which is what sparked the formation of the very first stars and galaxies. Without this invisible 85% anchoring the cosmos, ordinary matter would have just drifted aimlessly apart. Galaxies simply wouldn't exist, and well, neither would we. Section 2. Cosmic Clues and Footprints. So how did we figure all this out? Well, the realization of this missing mass was a very slow, century-long detective process. It kicked off back in 1884 when Lord Kelvin inferred that many stars near our sun must actually be unseen dark bodies, just based on their velocities. Jacobus Kapteyn expanded on this around 1922. But the real spark came in 1933 with Swiss astrophysicist Fritz Zwicky. Now, Zwicky was a brilliant but notoriously prickly scientist. He famously and kind of hilariously referred to colleagues he disliked as spherical bastards, meaning they were, bastards from every conceivable angle. Anyway, while observing the Coma cluster of galaxies, Zwicky noticed they were moving incredibly fast, like so fast that, based on their visible mass, the cluster should have just violently flown apart. He concluded some unseen dunkel materia, dark matter, was holding it together. For decades, the scientific community basically ignored him. It actually wasn't until the 1970s that Vera Rubin meticulously measured the rotation curves of spiral galaxies and proved that stars at the outer edges were moving way too fast. Standard physics said they should slow down the further they were from the center, yet the rotation curve just stayed completely flat. The absolute inescapable conclusion was that a massive invisible halo of dark matter surrounded these galaxies. That's what finally forced the world to take the missing mass seriously. This brings us to what is essentially the smoking gun in our investigation, the bullet cluster. It's the aftermath of literally the most energetic event we know of since the Big Bang, a hyperviolent collision between two colossal galaxy clusters. During this massive cosmic crash, the normal hot gas from the clusters slammed together. It experienced immense drag force, kind of like air resistance, and rapidly slowed down, heating up and blasting out X-rays. But the dark matter? It behaved entirely differently. Because dark matter doesn't interact with itself or with normal gas, it wasn't slowed down by the impact at all. It just kept moving right on through, basically acting like a ghost passing straight through a solid wall. This cosmic accident perfectly separated the normal matter from the dark matter, leaving the invisible stuff leading the charge while the normal gas lagged behind. It is direct, observable proof that a massive, invisible component of the universe exists completely independent of ordinary matter. But wait a second. If this dark matter doesn't interact with light, how on Earth can it be mapped so precisely in collisions like the bullet cluster? Well, the answer lies with Einstein's general relativity. Massive objects literally bend the fabric of spacetime itself. So when light from a distant background galaxy travels past a massive, invisible clump of dark matter, its path gets warped. It's actually a lot like looking at a candle through the curved base of a wine glass. We call this phenomenon gravitational lensing. By measuring exactly how much the light from those background galaxies is distorted and sheared into these stretched-out arcs, astronomers can mathematically reverse engineer the exact invisible mass causing the distortion. This lensing, when you combine it with the bizarre spinning speeds of galaxies we talked about, acts as the absolute, undeniable footprint of our invisible suspect. Section 3. Rounding up the suspects.
All right, so with the footprints firmly established, it's time to bring our suspects into the interrogation room. The very first candidates were actually really appealing because they were simple, just ordinary things that are incredibly hard to see in space. Astronomers called them machos, massive compact halo objects. We're talking dead stars, super dim brown dwarfs, or rogue planets made out of standard baryonic matter. They were the perfect suspect because they relied on known physics. But we actually had to cross them off the list entirely. Why? Well, the theory of Big Bang nucleosynthesis strictly caps normal baryonic matter at about 4 to 5% of the cosmos. If dark matter were made of normal protons and neutrons, the early universe would have cooked up a vastly different ratio of elements like helium and lithium. Just to be absolutely sure, astronomers conducted exhaustive surveys looking for the gravitational microlensing effects of these machos floating out there in the Milky Way's halo, and they barely found any. The conclusion was airtight. Ordinary, hidden matter simply cannot account for the missing mass.
Since it's definitely not normal matter, we are hunting for a completely undiscovered subatomic particle, and right now, we've got two leading candidates facing off. On one side, we have the heavyweights, WIMPs, or weakly interacting massive particles. These are hypothetical particles that only interact through gravity and the weak nuclear force. For decades, WIMPs were the undisputed favorite suspect. Physicists realized that particles with these exact theoretical mass and interaction properties, if they were created in the early universe, would naturally yield the exact abundance of dark matter we observe today. This beautiful mathematical coincidence became affectionately known as the WIMP miracle. On the flip side, we have the featherweights, axions. These are incredibly light, hypothetical elementary particles that were originally proposed back in the 1970s to solve a completely unrelated, highly complex problem in quantum physics. Axions are so unimaginably light that they would act almost more like a macroscopic wave just flowing through the cosmos rather than individual, discrete particles. Now, with WIMPs repeatedly evading detection at massive, powerful colliders like the Large Hadron Collider, the theoretical pendulum is actually swinging, and the wave-like axions are rapidly becoming a prime suspect.
Section 4. The modern underground hunt.
The sheer engineering extremes required to catch these theoretical particles, honestly, it's mind-blowing. To catch a WIMP, scientists are building these massive, ultra-sensitive detectors filled with freezing liquid xenon. Why liquid xenon? Well, it's incredibly dense, which provides a whole lot of atomic nuclei for a dark matter particle to potentially bump into. Plus, it's transparent, meaning any tiny flash of light from a collision can be easily picked up by sensors. Experiments like Lux Zeppelin and Xenon Anti are placed deep, deep underground. We're talking buried under mountains or installed way down in abandoned gold mines. They have to be completely insulated from the relentless, noisy bombardment of cosmic rays raining down from space every second. Down there in the quiet dark, the detectors just wait. The whole goal is to push interaction limits down by orders of magnitude, isolating the environment so perfectly that they can capture the unimaginably faint, singular flash of light that would occur if a dark matter particle just happens to collide head-on with a xenon nucleus. It is quite literally the ultimate game of cosmic patience and precision. Operating at this absolute bleeding edge of physics, it takes unparalleled international collaboration. This is a massive human endeavor. For these liquid xenon detectors to even work, they have to be the absolute cleanest, most radiation-free environments on Earth. Teams of scientists, like the folks working on the Xeno NT experiment, have achieved literal engineering miracles by filtering out background radiation, stuff like trace amounts of radon, to unprecedented, record-breaking levels. Pushing the limits of particle physics isn't just about throwing money at bigger machines. It's about hundreds of minds uniting across borders to clear out absolutely every conceivable false clue. By systematically eliminating the noise of our ordinary world, they get mathematically closer and closer to isolating the true, quiet signature of dark matter. So, with better detectors, sharper space telescopes, and some seriously brilliant theoretical physics, we are slowly, systematically boxing dark matter right into a corner. But think about this. When we finally do isolate the particle that makes up 85% of the matter in our universe, how is that going to change our understanding of reality itself? We'll have basically discovered an entire new realm of physics, a shadow universe that's been sitting right next to us, silently shaping our existence since the very dawn of time. The missing pieces of our universe are out there, just waiting in the dark.